Hi, in this video I will solve an elementary problem in complex algebra. We have the following question saying that evaluate the following absolute square of a complex number. And this problem arises in quantum mechanics. In the expression you see here, we have a and b, and we will take a and b to be real numbers. Question says, after that, express your answer in terms of a hyperbolic function. Now, as I said, this problem is elementary problem, and let's go through it slowly to understand how to solve it. Now, what is the meaning of this absolute square? We can write, in general, if I have a complex number, let's call it z, which is in general can be written as some real part plus imaginary part, we can then define the modulus of z, which we write it like this, the absolute value of z. Now, the square of that is defined to be the complex number z times its complex conjugate. Of course, multiplication is permutative, so this is the same as if you multiply z conjugate, the complex conjugate, times z. It would give you the same answer. So that's the meaning of this term you see here in the question, the absolute square. It means that we need to take the number inside, which let's call it z, and then multiply it by its complex conjugate. Now, what is the meaning of complex conjugate? A complex conjugate of a number, of a complex number, is simply the same original number, but we are switching the sign of the imaginary number I. So that's the complex conjugate of z. So now, based on that, this is elementary knowledge in complex numbers, let's try to calculate what is the absolute value, the square, the absolute square of this complex number. Now, the expression looks a little bit complicated, but we can calculate the absolute square of this complex number easily if we notice a few things. This expression is a complex number divided by a complex number. So now, we know that if I have a complex number, let's say z1, divided by a complex number z2, and I want to calculate the modulus, the square, absolute value square, then that's equal to the modulus square of the first number divided by the modulus square of the second. So that's one thing that we can use to simplify the expression. Another thing, we notice that the numerator is a difference between two complex numbers. So z1 minus z2, if I want to find the modulus square, well, that just means that z1 minus z2 multiply it by z1 complex conjugate minus z2 complex conjugate. Now, by multiplying the two brackets, we know that we will get easily z1 absolute value square. That's by multiplying this. Multiplying z2 by z2 conjugate will give us plus z2 absolute value square. And then we're going to get the mixing z1 times z2 complex conjugate with a minus sign. So you got z1, z2 complex conjugate. And then there's another term minus z1 complex conjugate z2. So we can use these two results to simplify the expression. Now, the expression above, now we can find the absolute square. So it's equal to the absolute square of the numerator divided by the absolute value of the denominator. Now, if you look at the denominator, it's very easy to find the absolute value. We got 4ab, and then we got I, and the exponential e to the minus ia. So now for later, we got 4a b I e to the, I guess it was minus, let's just check, yes. So minus ia, that's the complex number. Now let's multiply it by its complex conjugate. 4ab minus I e to plus ia. Now the absolute value of this is equal to 4ab, and that will be squared. Then we got I times minus I, that's 1, and the exponential e to minus a times e to plus a is 1, and that's it. So that was an easy expression to find. Now for the numerator, we notice that it's a complex number minus a complex number. So now we can use the result that we just found earlier. So the numerator, I don't need to write it really, but so the numerator is equal to the first complex number, absolute value squared. So the absolute value of this will be the absolute value of the bracket squared times e, the exponential e to the b, which is real. So the first term in the expression will be a square plus b square, and for the exponential it will be squared, so it will be e to the 2b. How did I get this? I just took this complex number and multiplied it by its complex conjugate. When I multiply a plus bi times its complex conjugate a minus bi, I'm going to get a squared plus b squared. Now this is already squared, and then the exponential e to the b will be squared. So that's the result of the first term. This next term, I'm going to find the modulus, or the square, the absolute square of the second term. So this is going to give me plus, again, the absolute value of the bracket. So I'm going to get plus, again, I'm going to get a square plus b square, which is squared, times the exponential, which is e to the minus b squared. So that will be e to the minus 2b. Now we did not finish, we still have the mixing. So now for the mixing, I'm going to get a minus sign, this number times the complex conjugate of the next one, of the second number. So I'm going to get minus, going to have this number multiplied by the complex conjugate of this. Now the complex conjugate of this term will be e plus bi, which is the same as the first number. So for the next term, which is the mixing, I will get minus a plus ib. Now this is already squared, multiplied by the complex conjugate of the second number, which will give us the same. So that's going to be e to the power 4. The bracket will be the power 4. And then I'm going to get e to the b multiplied by e to the minus b, which is 1. The last mixing term will be minus this term times the complex conjugate of this one. But that will give us a minus bi, same as this one. So the last term in the expression will be minus a minus ib to the power 4. And for the exponential, they will again cancel. So e to minus b times e to the b will cancel. So that's the numerator. We can simplify it again by, if we simplify this term and this term, now the result is very simple to find. So we simplify those two terms, and this way we find the numerator. We will divide this by the denominator. Let's continue just to find the final answer. Now let's simplify this further. The last two terms can be simplified easily in a straightforward way, and I'm going to leave this to you. Prove that a plus ib to the power 4, so we can expand this, plus the second term, which is a minus ib to the power 4. The answer is 2a to the power 4 plus 2b to the power 4 minus the 12 a square b squared. Gonna leave this for you to prove. And notice that the answer is real, as it should be, because the whole numerator should be real. Now we can simplify further the numerator by noticing that the first term and the second term, they have a common factor, and we got the exponential e to the 2b and e to the minus 2b. When you add them, that will give us the cosh function. Let me remind you about the cosh. Cosh z is e to the power z plus e to the minus z divided by 2. So using this result, now we can find the final answer for our question, which is this one again. Show you the question again. So the answer is, we prove that the numerator is a squared plus b squared squared times 2 times cosh 2b plus the last two terms that we proved previously. Please notice that if you go back to that expression, we get a minus sign. So I added the two terms here. So now when we substitute, we don't forget the minus sign. So the answer will be minus 2a to the power 4 minus 2b to the power 4 plus 12a squared b squared. So that's the numerator divided by the denominator, which we already proved and easily can be done to prove that the answer is 4ab squared. This is the final answer. This is the final result for our problem. And notice that the answer should be real, because that's the absolute value of the complex number. And we already express the answer in terms of the hyperbolic function cosh 2b. I hope you understand the question and you can go through these steps again. You can solve it in other different ways. You can, for example, expand these terms and then find the absolute value for the whole term again. And you should finally get the same answer as we did. I hope this video is clear. We'll see you in a different video talking about another problem in complex numbers. Thank you for watching.